Welcome back again. So, today we're going to see the KGA7 Phaedra DAU, or Digital Annealing Unit, Hyperparameters. The KGA7 interface page is located within the Play Now menu, on the KGA7 Phaedra item option. So, we'll click on that, right now. Right. So, once the interface is loaded, we can scroll down and see the various controls that are presented. As in the case of the Neural Reality Cube AI Engine interface page, you have to choose the lottery you wish to generate a prediction for. In order to do that, we need to select the region, the country, the jurisdiction, and, of course, the lottery. So, here, for this example, we're going to go ahead and choose a European lottery. On the region drop-down list, I'm going to select Europe. Now, the country drop-down list presents us a list of countries based on the region we chose above. In this case, European countries. So, I'm just going to choose the United Kingdom in this example. Now, just below, the jurisdictions drop-down list shows us a list of available jurisdictions, or districts, available for this country, the United Kingdom. You can see here, the system doesn't include lotteries that apply only to Scotland, England, Wales, or Northern Ireland as separate jurisdictions, but instead includes them all, so I will go ahead and select all. Once that's selected, we'll get a list of suitable lotteries, as shown here. For this example, we're going to select the EuroMillions lottery, which is available across 9 countries as of this video. The United Kingdom encompassing Scotland, England, etc. Okay, once we have that selected, we now get a lottery type description, in this case, 5 out of 50, plus 2 out of 12. What this means is that, in order to win the jackpot for the EuroMillions lottery, we have to hit all 5 numbers out of a pool of 50, and 2 bonus numbers out of a pool of 12. We are also presented with the last drawing within Neural-Lotto's databases for this lottery, at this particular point in time. The cost per run for the KGA7 Phaedra DAU system for this lottery, along with the total number of combinations that will be generated. Now, this is one of a series of points which differ from the Neural Reality Cube AI engine. The Neural Reality AI Cube engine can process all 261 lotteries at the time of this video, available to Neural-Lotto. On the other hand, not all of those lotteries are available to be predicted by the KGA7 Phaedra system, although the great majority are. The second difference is that, while the Neural Reality Cube AI engine will always output one combination, or even a string of numbers greater than the lottery base numbers, if available and selected. KGA7 Phaedra will always output a number of combinations, ready for play. The system calculates what is called a covering, which maximizes the chances for one or more wins, and creates a series of combinations to this end. In the case of the Euromillions lottery, KGA7 Phaedra DAU will output 9 combinations, all of them containing 5 numbers and 2 bonus numbers, ready for direct play. So this, right here, just gave us a huge advantage, which is not directly available on the Neural Reality Cube AI engine. Now, as we can see there, the first hyperparameter in this section is the history setting. If you've watched the previous video, you'll immediately notice that there is no learning rate hyperparameter here. This is because KGA7 Phaedra and the digital annealing unit, or DAU algorithm, does not typically use a learning rate parameter in the same way that traditional machine learning models, like neural networks and the Neural Reality Cube AI engine, do. With that out of the way, the history setting determines how many lottery data points are used to generate a prediction. Regardless of the total number of drawings, or data points, available, the system prioritizes the most recent data point specified in the history setting, which can range from 10 to 500. If the selected value exceeds the total number of available data points for a particular lottery, such as in the case of a newly established lottery, the system will use only the maximum actual data points available. For example, if a newly created lottery has only 50 historical drawings and I choose 500, the system will utilize the only available 50 data points, as there would clearly be no others to work with. If more than 500 data points are available, KGA7 Phaedra will emphasize the last 500. In this example, I am going to choose the last 150 historical data points as a good starting point. The next hyperparameter is stepping. The stepping parameter determines the number of historical data blocks used for training in a decremental manner, a process known as backstepping. Essentially, stepping and backstepping refer to the same concept. For example, if stepping is set to 10 and the history parameter is set to 100, training will involve 10 decremental cycles, or steps, per exploration attempt of the solution space. This means that the total number of exploration attempts is the product of the DAU algorithm's attempts at finding the solution and the stepping value. If stepping is set to 0, the parameter is not used. A good starting point for stepping is usually near the default value. The next hyperparameter is the combinatorial optimization scale. The combinatorial optimization scale on the KGA7 Phaedra Digital Annealer Unit, or DAU, defines the system's ability to manage intricate optimization challenges by converting the problem's variables and constraints into a binary format. Measured in bits, this scale reflects the maximum size and complexity of lottery combinatorial problems that the DAU can handle and process. It ranges from 10,000 to 100,000 in steps of 5,000. The higher the number of bits, the greater the system's ability to explore a vast solution space and find optimal or near-optimal solutions, up to a certain point, where the law of diminishing returns will start to kick in and hinder speed and accuracy. Once again, as with almost all hyperparameter settings, the default value is usually the best starting point, so I'll just leave it there. And now we have a toggle switch, the hobo to cubo hyperparameter. Hobo, or higher order binary optimization, to cubo, or quadratic unconstrained binary optimization, involves converting complex optimization problems with higher order variable interactions into a quadratic form. This transformation is essential because the KGA7 Phaedra DAU is optimized to solve cubo problems, which only involve interactions between pairs of variables. By converting hobo problems into cubo format, the DAU can utilize its computational capabilities to find optimal or near-optimal solutions for a broader array of combinatorial optimization challenges in lotteries. Now, it's important to remember that the hobo to cubo conversion process is vital because the DAU is optimized for solving cubo problems, which are mathematically simpler and more efficient to compute. By reducing higher order terms to quadratic terms, the DAU can leverage its computational power more effectively, ensuring faster and more accurate solutions. For this reason, the default setting is on and should generally be left on. The next toggle switch is the scaling and rounding hyperparameter. Scaling and rounding are techniques used to adapt lottery optimization problems into a form that the DAU can effectively process. Scaling involves adjusting the magnitudes of the problem's numerical coefficients to fit within the DAU's operational range, ensuring numerical stability and precision. Rounding, on the other hand, converts continuous or high-precision values into discrete or lower precision values that the DAU can handle. These processes are essential for accurately representing the problem within the DAU's architecture. Exactly as in the case of the previous toggle switch, the default setting of this switch is on, and should also generally be left on. Finally, the last hyperparameter is the cubo calculation size. This is a range spanning from 1,000 to 20,000 megabytes of problem data. The Cubo calculation size on the KGA7 Phaedra digital annealer unit specifies the range of binary variables and the complexity of their interactions that the system can manage while addressing quadratic unconstrained binary optimization, or QUBO, problems. This measure reflects the DAU's ability to handle and optimize combinatorial problems by representing each variable and its pairwise interactions in a quadratic format. Although you can set this hyperparameter to a single value by overlapping the controls, you should actually aim at setting a range, as this provides for optimum flexibility. The default is a range from 4,500 to 7,500, so I'll just leave this as it was. At the bottom of the interface, you will find a display field that indicates the investment required to run the DAU system. To cover this cost, you must select a suitable promo code from the available options in the drop-down list. It is important to note that the drop-down list will not display any promo codes unless you are logged in. If you are logged in, the drop-down will present a list of your purchased KGA7 Phaedra DAU promo codes. This list includes details such as the total number of uses, remaining uses, and expiration date for each promo code. Once you have selected a suitable promo code, you can then proceed to submit your request. So, that's all for today's tutorial, which covers the basics of how to use the KGA7 Phaedra DAU interface hyperparameters. Until next time, and thank you for watching.